Okay, perfect.
Okay, so Luca did his physics major in Naples, in the Universidad de Nápoles. Then he did his PhD in La Sapienza. And then I didn't know so many postdocs. He did his first postdoc there in La Sapienza, then in ICRA, also in La Sapienza, then in el IAA, el Instituto de Astrofísica Andalucía, with Antonio Dugarte and Cristina Tone. And then he got the Juan de la Cierva Fellowship. And now, well, since like the beginning of the pandemic, he's been in Copenhagen, being a dark, I love the dark fellow. And so Luca has been pretty much everywhere. And he then is interested in novas, in GRBs, in supernova emission mechanisms, in even cosmology with transients. And he's collaborated with, of course, Remo Ruffini, with Antonio Dugarte, Massimo de la Valle, un montón, tons of people. And I don't know, so it's been 2 Nature papers already, Luca, or how many?
No, well, I only one as a first total, yeah.
Yeah, okay, so Luca is pretty hot in the topic. And so thank you very much for being here and giving us this talk.
Oh, Diego, no, thank you.
And also Luca plays the bass really well. So he has tons of stuff to show. Ahora sí.
Okay, Diego, thank you very much. And thank you everyone here for, well, thank you for my presentation, giving me the opportunity to discuss one of the research line. Actually, well, I'm involved in many topics because I like to study all exploding things. And now with micronovas, maybe I know very well Simone Scaringi. He was a guest of mine when I was in Sapienza. But anyway, let's go back to the talk that we give today. Today, I would like to discuss one of the research lines where I'm most directly involved, which in particular in the context of high cadence optical surveys. Now at DARC, at the Niels Bohr Institute, I'm involved in the Young Supernova Experiment, which is an optical survey that uses the Pan-STARRS telescopes. And every day we are getting several new young transients. And in particular, the topic that I'm going to discuss today is very strictly related with the operation that we are going to do with this survey and also other survey incoming LSST. Actually, the main argument embraces 2 communities in astrophysics, supernova community and also the gamma ray burst one, given that the broad-lines type 1 C supernovae are the only supernova type with actually one exception, supernova type that is associated with gamma ray burst. Indeed, I will start my presentation with please just one thing. Stop me at any time because I would like to.
Yeah, I forgot to mention that. So is it okay if we stop you?
It's completely okay because I would love to receive feedback from you experts because I'm also collaborating with some of you. In any case, well, I will start with a short introduction on gamma ray burst, very short introduction, but I'm pretty sure that you know what I'm going to talk about. GRBs are very quick flashes of high energy radiation and are only detected from using space detector because of the high opacity of the atmosphere of our planet. And immediately it was discovered that they have a cosmological origin, in particular because their distribution after the operation of the BATSI satellite is completely isotropic, as we can see this plot, but also because after a few years from their discovery, it was discovered that a redshift was identified, a redshift from one of these events. So they are detected in the nominally in the hard X-ray energy range, which is the energy range going from 10 to 10 keV to 1 MeV. And the light curve, actually the evolution of the flux observed as a function of time of this prompt radiation shows a variegate morphology. We can have very regular pulses like Fred, fast rise, and exponential decay, or irregular short pulses, very short, or with precursor, with irregular morphologies. But as the evolution of the emission, the evolution with time of the emission moves from the hard X-ray to the soft X-ray to the optical wavelengths, we start to observe a more homogeneous emission, mainly characterized by a single or a double power law behavior. This is called the afterglow emission, which is whose origin is a bit different from what we observe from the prompt. It's just due to the relativistic forward shock emission due to the jet that interacts with the circumbus medium, jet that forms from the progenitor of these events. And actually, just a few words about what the spectrum emitted, in particular in the afterglow of gamma ray burst. As the jet emission interacts with the circumbus medium, it emits a synchrotron radiation whose emission is mainly characterized in a very wide energy range from radio to X-ray frequency by a different series of power law behaviors that are smoothly connected at break frequencies, whose value that evolves with time is mainly characterized by the electron distribution of the accelerated electrons in the shock. Maybe we'll come back later on this point, but one of the GLBs have been historically classified in two families, which is the division is mainly based on the duration of when we observe the 90% of the emission of GLBs during the prompt phase, and after building the cumulative distribution of GLBs, the value of the classification is based on 2 seconds. So GLB shorter than 2 seconds are called short, of course, and longer are called long. But this classification is not only based on temporal features of gamma ray burst, but also spectral characteristic of both short and long shows a bimodal distribution. So short GLBs are much harder, where for hardness we intend the peak energy of the prompt spectrum. So short GLB shows a peak energy much higher than long GLB event. And this evidence enforces the idea proposed in late 80s that short GLBs originate in the collapse of two compact sources, such as two binary neutron stars, as we know, particularly in the last year from the detection of the gravitational wave radiation that are associated with the binary neutron star merger, while long gamma ray bursts come from the collapse of a massive star, highly rotating massive star with a low metallicity. Sorry, here's some noise. But in both cases, we have the formation of a highly rotating massive black hole, or in some cases, it was also proposed a magnetar, particularly for long GLBs, highly rotating black hole that can emit a collimated jet that then generates the observed phenomenology in gamma rays, where the prompt emission originates from internal shock wave of the plasma emitted in the jet, while the afterglow visible from X-ray to radios is just due to the interaction of the jet with the circumburst medium. In this talk, I'm mainly going to speak about the collapse of the long GLB and the hypernova scenario. So, several observational properties of long GLB events pointed out in the past already a possible connection between these events with the collapse of a massive star. In particular, the total energy, isotropic energy, released in a long GLB event is almost comparable with the kinetic energy generally emitted in core collapse supernova explosion, particularly one silver line supernova. And another evidence that suggests that long GLBs come from the collapse of very massive stars is that they are generally observed coincidentally. They are generally observed in the brightest region of their host galaxies. And okay, this is just a famous, also older actually, collage of images obtained by the Hubble Space Telescope of some GRB's host galaxy. The cross corresponds to the position of long GRBs observed. You can see that they are generally observed in the brightest region of their host, and the brightest region generally corresponds to a large H2 region where stars form. Now, we know that, well, after a few years, that the progenitor star of long GRBs are massive stars of the order of with zero-age main sequence masses larger than larger or equal to 20 solar masses, and the age of this star is in general a few dozen of mega years, which is lower than the life of an H2 region. So in principle, we observe GRB in the region of their host where GRB die where they actually born. And the study of the H2 region close to the position of GRB is also a proxy for studying the composition of the progenitor star of GRBs. I will be back later on this point. So the first clear connection, sorry, some noise, between gamma ray burst and a supernova was by now famous case of GRB 980425. I think that you already know how GRB are named. So it's six numbers where the first two correspond to the year of their discovery, the second to the month, and the last two digits to the day of their discovery. And this gamma ray burst was observed the year after the discovery, because the identification of the first redshift from a gamma ray burst. Currently, this event is the most nearby GRB ever known, and it has also some peculiarities. So it is a low luminous gamma ray burst. So its isotropic energy to the order of 10 to the 49 erg, which is almost 2-3 order of magnitude lower than the average isotropic energy emitted by left cosmological gamma ray burst. And after the discovery of these events, its optical light curve showed after a few days a rising emission that was later on thanks to the optical spectra of this rising emission that was identified as a broadline type 1c supernova. Another characteristic of this event is that it's associated supernova as a large 56 nickel mass. You know that the 56 nickel is an isotope that powers the luminosity of supernovae, also type 1a supernovae, and its mass is almost comparable with the average value of nickel 56 nickel emitted in type 1a supernovae. And another point that was observed during the nebular phase of this supernova with late spectra. The nebular phase is when the ejecta is completely frozen, so the shape of the emission lines, because all the spectrum is recombining, so we can actually have a guess on the actual geometry of the ejecta. And the profile of some emission lines is not very clear in this image. I do not have an image to show, unfortunately. But on the profile, the study of the profile of the main lines, if I remember correctly, was a forbidden iron 2 line, showed an asymmetry, no, oxygen 1, sorry, an asymmetry in, so it's not a Gaussian, an asymmetry that was pointing out an aspherical ejecta for this supernova. So I have mentioned so far 1C broadline supernovae, type 1A supernovae, but I think that it will be, it is necessary a short clarification between the different types of core collapse supernovae, because each single type, as for gamma ray burst, corresponds to a different progenitor. So type 1A supernova are thermonuclear supernovae that are emitted from the thermonuclear disruption of a white dwarf, and it's not a core collapse supernova. But we have most three main classes of core collapse supernovae. Type 2 and all these classes are characterized by the presence of some particular peculiar features, emission or absorption line features in their peak brightness spectra. Type 2 supernovae shows Balmer line, P Cygni of Balmer lines, hydrogen lines, H alpha, H beta, H gamma, and so on, were characterized by blue shifted absorption and more brighter emission line. These class of supernovas are also named as interacting supernovae, and their progenitor are in general massive red supergiant star, that still maintain the external layer of hydrogen. Then Then in the case we do not see hydrogen line, but we have the presence of neutral helium feature, we have the type 1b supernova, whose progenitor is a Wolf-Rayet star of the nitrogen sequence, WNL, WNA. So a core that after its evolution from the main sequence formation, it has lost. It was stripped by the external hydrogen layer, but still preserve a smaller amount of helium in its most external layer, more or less 0.2, 0.3 solar masses. And then we have the type 1c supernova, whose progenitor is still a Wolf-Rayet, but completely stripped also of the helium layer. In some cases, we also have hints of presence of faint helium lines in type 1c supernova, but it's generally assumed that the progenitor of this class of supernova is a carbon-oxygen core, or the Wolf-Rayet of the carbon-oxygen type. And supernova associated with gamma ray bars are of the type, show all the features of a 1c supernova, but their absorption features are much broader, so with a larger velocity distribution for each absorption line, and also display a larger ejecta velocities. Now, the ejecta velocity is mainly computed from the difference in wavelength from the rest frame wavelength of the line and the minimum of the corresponding absorption. While type 1c display an average velocity at peak of 10,000 kilometers per second, the 1c broad line have an average velocity of 20,000 kilometers per second, and this implies also as a consequence on the kinetic energy emitted in these events. Now, I want to mention another couple of cases of GRB supernova connection. Another one is the second spectroscopically discovered GRB supernova that happened 5 years after 980425. And it was 0329 at redshift 0.716. That was a cosmological GRB in terms of the isotropic energy emitted. So in the gamma rays, 10 to the 53 egg. And the fact that was so bright also implied that its X-ray and optical afterglow was very luminous. Indeed, in order to identify the underlying supernova, it was necessary to subtract the afterglow component from the total observed emission. This the central panel, it is indeed shown as black bars, the global optical afterglow, while with dashed M dot lines, the afterglow and the supernova component. Actually, the black data are the composition of the two components. And also for the spectra, it was necessary to subtract the afterglow component. Actually, this is not a complicated job, because generally, as we have seen, the spectrum of GRB afterglow also in the optical is a simple power law behavior. So you only need to subtract a power law whose index is mainly given by the X-ray observed afterglow. So in general, the slope of the afterglow in X-ray corresponds to the optical at late phases. This is always what Jens Hjort, I think, was the one that published this paper, made for the discovery of the supernova, and the underlying supernova connected with 03329 showed exactly the same feature of 98 or 98 BW that was the supernova associated with 980425.
Sorry, Luca. So here, sorry. So I have two questions. Can you go back? So first is, and do you know, has anyone commented on like at 2 months, there seems to be like another bump in the light curve in that central,
You mean here?
Yeah.
I don't think it's another bump. I think that this is the level of the host galaxy, because at a certain time when the light decays, this is a very quite nearby GRBs, but you arrive at the that the flux coming from the host galaxy is almost comparable to the flux of the optical after. So you start to have a sort of flickering.
Okay.
But yes, I will check better if this can be the flux of the host.
And then the other thing that from your right plot, but Galama's 98 GRB isn't it really like a outlier, and it has really low energy, no?
Yes.
So it's rather striking how in the previous plot, 98 BW and this 2003 that has, on the contrary, tons of energy, are so similar in the spectra and how they evolve. So I've never really understood how, if Galama's is really weird.
It's not only Galama, also this other one, 06028, sorry. Oh, okay. Yes, your question is crucial actually, because there are several explanations. So in the case of 03029, we very likely we have observed the jet on axis. So the jet was pointing on our direction. For 980425, that was 4 order of magnitude lower in energy. Actually, there are two different explanations. One is that we have observed the GRB slightly, the jet slightly off axis. So we have missed the bulk of the gamma ray radiation, or maybe we have observed, as Piran love to say, the shock breakout. So it's not exactly the jet, but well, it's just the breakout from the supernova. But okay, for 980425, when it was discovered, there were no X-ray detector that were able to point immediately after the discovery of the GRB in order to search for an X-ray afterglow. So the afterglow was discovered 6-7 hours after the GRB event. So we don't know exactly, so we do not have the knowledge as for 06018 of the X-ray emission.
Okay. So it might have been off axis and it might have been the shock breakout.
Yes, exactly. But this, I will go back to this point. Also now for the case of 06018, that was is actually the third closest long GRB ever known so far, and its isotropic energy was similar to 980425, so on the order of 10 to 14, maybe also lower than 980425. Its supernova associated with 2006 AJ that you can see. As for the previous case, the spectra at the peak shows very similar shape of the other supernova, similar absorption line, the silicon line, the iron, and so on. But its high energy light curve was really peculiar. So I hope to display very well the emission from this GRB. So it was detected as an image rate by the Swift detector. So actually it was very faint. And its prompt emission lasts for more than 3,000 seconds, but was at the same time very soft, and a detailed analysis showed the presence of an underlying thermal component that lasts for the entire duration of the prompt phase. And the X-ray emission, X-rays is shown here. Below you can see the ultraviolet and optical light curve. These are the light curve from the Swift satellite. Swift has three different detectors. One is the Burst-Thales telescope that detects GRBs in the hard X-ray energy range. Then there is this XRT telescope that is able to point, to move the to point to the region where a GRB has been observed after 1-2 minutes. So in principle, we can have the information very soon. There is a gap from the T0 and the first X-ray data, and this is the time when the the time that the satellite needed to slew and point the position of the GRB. And then, in addition to the X-ray emission, there is an ultraviolet and optical telescope that can observe in the UV and optical range from 2,000 angstrom up to 5,000 angstrom using 6 different filters. And here you can see how the gray data corresponds to the contribution of the thermal emission on the global X-ray, the black data, the total X-ray observed photons. While here you can see how there is a first component peaking after in the first day after the GRB detection. Yes, 10 to the 5 seconds first day. But you can also see how that the first, unfortunately, there is no legend here. I forgot to include the legend, but the first peak was at UV wavelengths, and then the peak moved to the optical range. Here we have the secondary peak after 10 days that corresponds to the supernova. And this event has been interpreted as a shock breakout from the, yes.
Sorry, Luca. In the first one in 98/4/25, you gave us the kinetic energy or the velocity of the ejecta of the supernova,
yeah,
and an estimate of the energy. Do you have those numbers just to so I can recall what it is for 03/03/29 and for 06/04/18?
So you want the kinetic energy for also this supernova?
Yes, for the type 1c.
I don't remember, but don't remember now. But
because I imagine that the GRB may depend a lot on, like you were mentioning, on the angle. However, the supernova might be a better comparison. If the angle is changed, the supernova is not, it may be asymmetrical, but it will not be as asymmetrical as a jet.
Yes, completely agree with you. I don't have the number, but I don't have also a plot, I'm sorry. But the supernova associated with 06/02/18 is one of the faintest supernova in terms of luminosity, energy emitting optical radiation in light. One of the faintest GRB supernova in all, but the difference is a factor of 1.5 magnitude actually. So 1.5 magnitude corresponds to a factor of 3-4 in terms of luminosity. About the kinetic energy, yes.
So it has much less nickel then.
Yes, exactly, because the peak, the nickel 56 regulates the brightness peak of the supernova according to the Arnett law. If assuming spherical symmetry, and from the Arnett law, you can, well, if you build the bolometric light curve, you can also compute the total kinetic energy, but you need a crucial information, which is the velocity at the peak. And the velocity is generally inferred from the minimum, the absorption, the minimum of the absorption of the features that you observe in the optical spectra. I don't have this number, but maybe I can address you some publication. There is there are many papers about 06/02/18, but there is a paper by Joe Lyman in 2016 where he made a review of all 1C broadline supernovae associated and not associated with gamma ray bursts with several properties. He also made, actually he also found a typo in the original Arnett formulation. He corrected this typo, and so you can find the most accurate data. It's a paper by Joe Lyman in 2016 monthly notices.
Right.
So yes, actually this emission was originally explained as a shock breakout just a few words about it. I've included this slide trying to explain what is the origin of this shock breakout. It is actually the first emission that we observe from the core collapse of a supernova, because you know that when you have a core collapse supernova, you have this onion layer structure with the heavier element at the center and the lighter on at the most external layer. But at a certain time, you have that when you have the formation of an iron core, the iron core cannot support the gravitational potential, the gravitational energy of the above layers, and indeed it starts a collapse. When we have the collapse, matter rebounds onto the newly formed neutron star that at the same time, by the inverse decay process, emits a huge flash of neutrino, 10 to the 53 erg energy of neutrino. And this neutrino is powering a shock wave that propagates outward onto the progenitor stellar layer. And as the density decreases, these shock waves start to accelerate according to the Rankine-Goniot relations until it reaches the photosphere, where the density, let's say, drops almost to zero, and a flash of UV or optical radiation is emitted, and it is the shock wave, the shock breakout. However, in gamma ray burst supernovae, we have also another more important component. Well, as almost all things in the universe that rotate, all things in the universe, from galaxy to star, planets, they rotate, also massive stars rotate. And when they lose the most external layer, like hydrogen, helium, its angular momentum automatically increases. So in the case of Wolf-Rayet of the type CO, we can have the formation of a fast rotating iron core. If the progenitor is also characterized by a particularly low metallicity, because mass loss is metallicity dependent, we can have at the core collapse the formation of a highly rotating black hole that can power the jet. And this jet that happens almost seconds after the core collapse also can interact with the stellar layers, and its interaction leads to the formation of an internal cocoon. Yes, okay, well, I was just anticipating what I'm going to mention here. As the jet propagates within the stellar layers of the progenitor star, we have the formation of this sort of cocoon that is composed by two components. One is the stellar shock component traveling at, well, in the stellar layer at lower velocity than the shock the jet material. And during this propagation, the jet can deposit a huge quantity of its energy into the cocoon itself. Another property of this cocoon component is that it should be composed by iron peak elements, so elements that are synthesized by the in the most internal region of the star during the core collapse, because the jet actually is transporting matter from the most internal region of the star, and during the jet works like a sort of mixing mechanism, so it enriches the cocoon of material produced in the most internal region, so heavy elements. This is a simulation made by the HEAP-UNAM group, where it is shown the propagation of a jet in a GRB supernova. The upper panel corresponds to the density, the lower panel to the velocity. As you can see that when the jet reaches the photosphere, the cocoon starts to spread laterally, because it is not more collimated by the stellar layer. So the density drops almost to zero, and the cocoon can expand laterally, while the jet still maintains its collimation due to the, well, there are more experts than myself that can explain why the jet can keep its collimation due to self-magnetic field, probably. So what are the main ingredients? So what do we expect to observe during the very early phases immediately following the jet cocoon breakout? And what are the main cocoon signature? So in principle, when the cocoon breaks out, we expect, similar to the shock breakout, a prompt flash of X-ray UV radiation rapidly cooling to longer wavelength. Moreover, since this cocoon is powered by the jet itself, and it has a large, well, it's still a fraction, 0.1 almost, the total energy of the jet, it should have, but the density is much lower. It should have a larger, it should be characterized by larger velocities in the ejector. So we should expect to observe features traveling at very high velocity. And another characteristic is that when we are going to model the cocoon emission, we should expect a larger contribution from heavy elements like nickel 56 and its daughter elements like cobalt and iron 56. That you know that if nickel 56 is highly unstable, that decays in 7 days. But anyway, with half-lifetime decay of 7 days. And we believe we have observed all these ingredients in another gamma ray burst, 171205A, associated with the supernova 2017 IUK, a GRB that was detected by SWIFT and was characterized by, similarly to 980425, by a very low isotropic energy and a very low luminosity pulse in the hard X-ray range. Indeed, the X-ray light curve was equally fainter, showing the canonical 3 power law behavior. Actually, when the evidence that we observe high latitude emission at the beginning of the X-ray light curve, followed by a plateau and a late power law decay, this is actually the plateau and the late decay is what we expect from the external shock from the jet, the external shock emission from the jet that interacts with the circumburst medium. However, why we should expect a similar behavior, we should have expected a similar behavior at optical wavelengths, but the data obtained with SWIFT and other on-ground telescope, because we start immediately an optical and spectroscopic campaign to follow these events, was one of the most nearby GRB supernova known. The optical behavior was completely different from the X-ray behavior, pointing out to the presence of another component immediately following the GRB emission. And you can see that after a few days, this is the rising supernova that peaks 10 days after the GRB trigger. So, oh, sorry. Thanks to the multi-wavelength campaign, we have built different spectral energy distribution using X-ray and optical and near infrared data that we collected using space and on-ground telescope. And from the multi-SED distribution, we have found the presence, we have found that this SED could be modeled by a power law function that is the X-ray, the GRB afterglow emission, with an external contribution from a thermal component modeled with a black body model. And using this modeling, the first 2 days of the emission of this GRB, we are also able to reconstruct the luminosity, from the luminosity observed and the normalization of the black body, we could infer the temperature and the radius of the evolving black body. With at the beginning, immediately 1.5 hours after the GRB event, we found that the black body, using a non-relativistic model for the thermal component, a radius of 10 to 12 centimeters, 1 order of magnitude larger than the typical radius expected for a carbon-oxygen core progenitor star. Okay, and this was one of the first hints for the presence of a cocoon. But the main breakthrough came from the spectroscopic observation. Indeed, the first day spectra that were obtained using OSIRIS mounted on the Gran Tecan telescope in La Palma showed the presence of broad ondulation already 1 day after the GRB explosion. And our modeling we model this and also we demonstrate that these absorption correspond to silicon-2 and calcium-2 triplet, the infrared triplet at very large velocity of the order of 100,000 kilometers per second. This is the second hint that for the cocoon, the presence of large velocity. And how we model this? We use the Monte Carlo radiative transfer one-dimensional code called TARDIS, which is widely used in the supernova community because it's very fast and it also is able to solve the radiative transfer equation just using this random walk Monte Carlo approach. But it makes some assumption, of course, because it's fast. It assumes homologous expansion, so upward flow. The radius can be proxied by the velocity times the observed velocity multiplied by the time from the explosion. It assumes spherical symmetry for the ejecta and is a one-dimensional code. So in principle, in order to model the cocoon, we made a sort of, well, we made some approximation. TARDIS, in order to model an entire evolution of a supernova, in particular during up to the peak phase, because after the peak we have additional effects that are not taken into account in TARDIS. You need the knowledge of the bolometric luminosity of the supernova, and we obtain this from the multi-wavelength observation. We need a density distribution for the ejecta and an abundance pattern. So just playing with this parameter, you can model your supernova explosion, but it's very time expensive. So you need a power well, despite that this is very quick, very fast, you still need a very good machine to find best solution, the best model for your spectral evolution. Here is shown another supernova that I modeled recently, another type 1c supernova. And for the case of 2017 IUK, we have built our own model, which is very similar to the CO138 density distribution model that was used by Iwamoto et al. To fit 98 BW, but we have considered an extra density at a larger velocity, larger than 50,000 kilometers per second. Remember that since TARDIS assumes homologous expansion, velocity is like a proxy for the radius, for the radius, yeah, the radius of the ejecta, the distance of the ejecta from the GRB. It depends on the time that you are modeling the spectrum. And with this model, we were able to simulate almost precisely the spectral evolution of the supernova associated with this GRB, and also the first two spectra that were dominated by the cocoon emission. And our model shows an enhancement in iron peak elements compared to the supernova density, taking into account that the supernova is characterized by lower velocity of the order of 20,000, 30,000 kilometers per second. At a larger velocity, we have the cocoon domination, which also dominates at early times. And when you have an ejecta dominated by nickel 56, you also have a much bluer spectrum, which is indeed what we have observed during the cocoon emission. And according to our modeling, we have estimated a mass for the cocoon of 0.13 solar masses, which is just simply the integral of the density distribution at larger velocity, larger than 50,000 kilometers per second, and a total kinetic energy of 10 to 52x, but take into account that the kinetic energy is dominated by the large velocity that we have measured at these epochs.
Sorry. So I have a question. So can you go back one? So you're saying this density profile is, how does this go as a function of radius? Like, is it 1 over, like, is it a mass density? Like, is it 1 over r squared, or how is this as a function of radius? Like, is there wind there, or is the density constant?
No, the density, well, this is a density as a function of velocity, but you can transform as a function of radius just, this is the density distribution at 20 days from the explosion. Of course, if you have a density at 1 day, the value here will increase because density decrease with time. But in order to recover, but TARDIS needs a density distribution at a given epoch that can be 1 day, 10 days, 100 days, and the shape is preserved. Like, for example, well, one of the assumptions of TARDIS, that the shape of the density distribution is preserved, but actually what evolves is the time. So you can recover your rho of R function just multiplying the velocity, the x-axis, by the time. In this case, it's in days, but you should multiply it in seconds, when you have built your density distribution. I'm not sure I was clear, Diego.
It's what, so if you would multiply that velocity times the days, do you get like a wind-like medium? Like what has the medium been impacted by a wind, and so you have 1 over R squared, or is it more like a constant density?
No, was not R to the square. The index in velocity was -2 to the -6, if I remember correctly, in our case.
Okay, so the medium is varying as a function of distance.
Yes, exactly. It's not a constant, just varying.
Okay, okay. Thanks, Luca.
A quick question before you move on up. You mentioned the kinetic energy here, that 10 to the 52 ergs. How does that compare to, from your afterglow modeling, the true jet energy for this source? Do you have any idea?
The true jet energy, you mean?
Yeah, yeah, the energy of the jet, right? You did some afterglow modeling for this source as well?
We didn't make an afterglow modeling for this source, but what I can mention to you is that the isotropic energy.
Okay, even the isotropic energy, do you know?
Was lower. Indeed, one possibility is that actually we have observed this GRB is slightly off axis, and I can show you later slides. Well, I put in the appendix these slides because recently some colleagues has done the modeling of the radio emission of this GRB supernova along 3 years of observation, and they found the press that it is well fitted by a cocoon plus an off-axis jet, slightly off-axis jet afterglow. But about the energy, I'm sorry, I don't remember how, but just you need to integrate the X-ray luminosity over the time of the duration.
Mm-hmm. And
I remember that was the isotropic energy was the order of 10 to 49, 10 to the 50 erg.
10 to the oh, wow. Okay, it's like 3 orders of magnitude smaller, right? Compared to the kinetic
energy in the gamma ray in this event,
right?
In this in the prompt emission. Right. I don't remember in the X-ray. Sorry, I'm not prepared.
And what kind of off-axis angles? I mean, you mentioned several cases where you think that you're observing off-axis jets, but what kind of off-axis angles are you finding? Do you have any idea?
You mean the inclination? Inclination is few degrees, because we were able to observe the X-ray emission, the plateau and luminosity just few hours after the GRB. You know that as the jet is more the angle of the jet along our line of sight is larger, you have that the jet will enter along the emission of the jet will enter along our line of sight later on. So we should observe a rising emission if the jet is more elongated along our line of sight. In this case, we observe 2-3 hours after the GRB clearly the emission from the afterglow. So if it's off axis, just a factor of few degrees. But since this is a collimated emission, the Doppler boosting has an important effect. So you can have a large decrease, maybe Fabio can correct me myself, you can have a large decrease in flux also if your jet is off by 2 or 3 degrees more or less, or maybe factor of few degrees from our line of sight.
Okay. All right. Thank you.
Okay, is there another question? Well, this is the modeling with TARDIS, and the third, yes, Fabio.
I have a question too. So the kinetic energy that you're putting here is just the kinetic energy of the cocoon?
In this case, yes, only of the cocoon. But we have also estimated one from the supernova. I don't remember if it's here. No, probably not. But in the paper is mentioned, we use the Arnett modeling of the supernova emission.
Okay, because those kinetic energy and the cocoon mass are very large now. Also, you mentioned before that the cocoon energy should be 10 to 50, 10 to 51. So how the fact that you are assuming the spherical symmetry affects the predictions?
A lot, because, well, this is a one-dimensional code. Very good question. We did not quantify the effect of the spherical assumption.
So is it possible that assuming that considering an aspherical cocoon, you would get a factor of 10 lower or not? Or
it is possible. Yeah, okay, I get your, so okay, I get your point. Yes, it is possible. I didn't think about this possibility. So this is a density distribution if we assume a spherical geometrical distribution, but actually the cocoon is not spherical, it's not 4 pi, should be lower. Yeah,
so
it could be.
Okay.
Yeah, it's an upper limit, yes, than 52. But, well, remember that the kinetic energy is mainly driven by the square of the velocity. So the velocity here is 5 times larger than a typical one C broad line. So we have a factor of 25 more or less.
Okay.
Larger than a typical. So, well, yeah, something that should reconsider. Yes. Thanks for your comment, Fabio. Let me take some notes. Okay.
Spherical cows, Luca, always.
Say again, Diego?
Spherical cows.
Don't speak about the cow, please. And okay, this is another slide showing this is a test that Keiichi made the modeling with TARDIS, Keiichi Maeda. The gray dashed line corresponds to the expectation from the CO138 model, the one that best fitted 98 BW, while the stars are the results from our theoretical simulation, so our model. You can see that there is a difference, in particular in the first 2-3 days when we have the first 2 days when we have the largest contribution from the cocoon emission. With respect to the later epochs, the 10.95 corresponds to the peak of the supernova emission, and the prediction from the two models are almost equal. But actually, because we are integrating TARDIS, we are integrating the equation in a velocity range that is almost very similar. But another interesting plot is this one. This is mainly observational. It shows the minimum of the absorption lines of this should be the silicon 2 features for different GRB supernova events. Actually, 2017 IUK is the only GRB supernova event for which we have a great spectral coverage in the first 4 or 5 days after the GRB. All the other GRB supernova have been observed after 4 or 5 days, when actually the cocoon contribution was almost gone. And indeed, all the velocity evolution also is almost coincident, but at the first epoch, 2017 IUK show a rapid increase. And it is very possible that also other GRB supernovae could show similar increase of the velocity due to the cocoon emission. And one, we are, with some colleagues, we are already studying other well-observed GRB supernovae. One of these is 1612-19b, where there is a nice paper by Zach Cannon in 2017. And actually, in the G-band light curve, he pointed out also in the paper the presence of a pre-bump anticipating the main supernova emission. And this spray bump could be likely due to some cocoon-like or similar emission. Okay, now just to, let me check the time. Oh, it's really late. I'm talking too slowly. Just to mention that among all the core collapse supernovae, all the family that I mentioned before, the one that the one C broad line, the class that is associated with GRB, correspond to the 1% of the total number of core collapse supernovae. But not all 1C broad line are indeed associated to GRBs. A large fraction, the majority of these events, 80 to 90% of 1C broad line, indeed are not associated with the GRB or to any collimated emission. So in principle, seems that probably there is no, well, if they are not associated with an observed that detects GRB, in principle, someone can argue that there is no associated relativistic jet component. But however, if you look at the spectra of two GRB supernovae, like 98 BW, 2006 AJ, and two 1C broad line supernovae that were not associated to any GRB, the supernova spectra are very similar. Similar feature, silicon line at similar velocity. In particular, for 97 EF at the peak, it showed very large expanding velocity of the order of 25,000 kilometers per second. Another interesting, supernova, historical searches at radio frequencies, okay, despite this is quite old, it was made 15 years ago, show that 1C broad line supernovae, but in this paper the search was limited to only 6 cases, were not associated to with any known GRB, in particular at radio frequency. You know that the afterglow emission from a jet peaks at later times in the radio. In principle, if you want to search for an afterglow emission from a 1C broad line supernova, it's better to find, particularly if they are very nearby in the radio, because you can observe the peak of the afterglow moving at this frequency. But Alicia Soderberg showed that for the sample of 1C broad line that she considered, they did not show, she only obtained upper limit also for different elongation of the jet along our line of sight. And also, most recently, for the quite nearby 2014 AD, Marco Marongiu also found upper limit in the radio, but in principle, using a modeling sorry, of the radio afterglow, they did not exclude the presence of a narrow jet that was offset along our line of sight of about 30 degrees. So, so it seems that the majority, according to what I showed before, the majority of GRB-less 1C broad line supernovae are actually not accompanied by collimated emission. However, as we have seen before, the spectra of 1C broad line, GRB-less 1C broad line supernovae show excess at high velocity. That, well, someone also, in particular, Piran and colleagues, have interpreted of a signature of a choked jet. What is a choked jet? So choked jet is a jet that is not able to escape its progenitor star because the central engine that powers the jet components at a certain time stops to feed the jet itself. So the jet is like dies inside the stellar material, but its early interaction, its energy is automatically entirely transmitted to a cocoon component that continues to propagate because you put a perturbation inside a density material. This cocoon propagates inside the stellar layer until it breaks out from the star and start to accelerate because of the density decrease. This is another stimulation by Hudnaka showing a choked jet. We have the formation of a jet from a central engine that at a certain time is stopped to feed the jet itself. The jet choked inside the stellar layer, but it continues to propagate within the star until the density decreases, until it breaks out, emitting a flash of UV decaying optical radiation and emitting these oblated component. And so actually, I'm going now to talk about this event, is supernova 2020 BBC, that was not associated, 1C broadline supernova that was not associated to any GRB, was also quite nearby, more close than 060218, but not 98 BW. And it was discovered as by the Assassin survey as a decaying source. Generally, when we observe a supernova, we observe a rising emission. But in cases when we have shock breakout or also cocoon, we observe a decreasing emission that after a few days start to rise, showing the peak of the classical supernova. Interestingly, spectra obtained with Floyd and the Liverpool telescope show the presence of broadline features that we have interpreted as silicon 2, iron 2, different colors correspond to the absorption of different transition and comes into the near triplet at 70,000 kilometers per second at 1.5 days after the expected collapse of the supernova, and 4 days at 35,000 kilometers per second at 4 days from the collapse of the supernova. But more interestingly, this supernova displayed an X-ray detection. So it was identify an X-ray emission by Chandra in Swift XRT and also in the radio at the position of the supernova. So, and what is interesting is that, sorry, the X-ray emission, well, there was a target opportunity. So, you know, everyone can ask Swift to observe any source if you have a good science case. Someone, I don't remember, maybe we also activated Swift, I don't remember at the moment, maybe Katie, a colleague of us. Someone activated the Swift to observe in UV and optical frequencies and also at X-rays. But in the first 2 days, there was no X-ray emission report by Swift. But an emission was observed 3 days after the expected explosion of the supernova, and it was much brighter than the previous upper limit. We also, using an hardness ratio analysis, we estimated that the photon index was similar to what is expected for a GRB afterglow, and using multi-wavelength analysis, thanks also to support of Fabio, we demonstrate that these radio and X-ray emission could be explained as an off-axis GRB. Okay, sorry, as an off-axis GRB with an inclination angle of Fermat of 23 degrees, more or less. And the best model was with a wind parameter of 1.5. And actually here it is shown also the case for different other 1C broadline not associated with a GRB. So the best explanation is that the first decaying optical emission was indeed the shocked stellar material shocked by the jet itself, and our location compared with the direction of the jet is such that we have observed only in the first 1 or 2 days the optical emission from the shocked stellar cocoon. So after this event, we have started a search also within the Young Supernova Experiment and other survey for similar signatures in 1C broadline supernova, mainly pre-supernova bands. And we have found some cases. I want to show only one interesting event that was discovered last month. 2022 EQB was discovered by Atlas. This is an upper limit by the same Atlas, then showed a first rising emission. Then a first spectrum was obtained here, just about 10 days from the first detection. And the first spectrum, this blue curve, showed broad ondulation typical of broadline supernova. Indeed, this event was classified as supernova 1C broadline. Then we activated Swift to get UV and X-ray emission, and the UV data displayed a rising phase followed by decaying. So it's possible that this event was a sort of pre-supernova bump similar to a shock breakout jet-cocoon. And then we have the canonical supernova emission. However, late spectra continue to show the same undulation, the same broad feature, just with a lower expanding velocity. I have estimated an expanding velocity of 25,000 kilometers per second. This is really an interesting event that we are studying currently. And actually, we have also measured an upper limit from our Swift XRT data of 2 × 10⁻⁵ millijansky, and using a modeling with Afterglow Pi, this Python free code that is can compute light curve from light curve emission for different inclination angle and for different jet structure, but only for the constant ESM case. Unfortunately, we could not constrain the angle because our preliminary flux, we are still trying to improve our measurement. Actually, is this position if compared with the different light curve of Afterglow for different inclination angle. Unfortunately, we triggered too much late the Swift, but the supernova was discovered already 10 days after the explosion. So just some unlucky, but there are other interesting cases that maybe I can show on another occasion. Yes, I mentioned before that, but for the Afterglow, that cocoon can also be observed at radio frequencies. And with Fabio and other colleagues, we have an active proposal at Attica to check, to identify cocoon feature in the radio, because cocoon should anticipate the supernova emission at radio wavelengths for both 1C broad line and also for GRB less and for GRB supernova events. Last few slides. Another way to study the connection, the possible connection between choked jets or GRB supernova, jet cocoon in different 1C broadline supernovae is given by the study of their host gas, in particular in the immediate environment of these events. So there are previous studies made just study the integrated light from the host galaxy of 1C broadline supernovae and GRB supernovae that showed that the metallicity of the gas of the star-forming region in the galaxy is much higher for GRB less supernovae than for 1C broadline, for which there was an accompanying detected a collimated emission. And this can be just explained by the fact that when we have a progenitor star with a larger metallicity, so the large metallicity implies a significant mass loss for the progenitor star, and then a lower angular momentum for the final iron core that is going to produce to collapse and produce the GRB jet. So in principle, we should expect, as observed here, higher metallicity in the H2 region for 1C broadline supernovae if compared with GRB supernovae. However, these studies have been done using integrated spectra. So an idea that we are developing with Christina and other collaborators consists in using IFU integral field unit detector to study the immediate environment where these supernovae have been observed, so that studying using spectral synthesis code, the spectrum at the location of the supernova, we can not only infer the properties of the stellar population, but also study the pure nebular gas spectrum and then derive metallicities using emission line indicator. So finally, I'm almost gone. last slides, why it's important. Just mention why it's interesting and important to study these events, because for this class of supernovae, the jet can have an important role in addition to the canonical neutrino heating mechanism. And the characterization of cocoon emission, as well as the same optical jet, can really help us in understanding the role of the jet in 1C broadline supernovae, and eventually find other interesting properties of these events. So, well, I talked too much, 1 hour and 10 minutes. Thank you very much for the attention for people that are still online. Thanks a lot.
Okay, so please raise your hand if you have questions.
I have one, but I'm waiting for someone else to before I start.
I think that Enrique have a question.
I do have a question, but I don't mind going after Diego also.
So,
all right. So we know that these progenitors are massive stars, and we have, as time goes by, especially in the last decade or so, more studies that show that such massive stars will hardly ever be single stars, but they will actually be doubles, triples, maybe even quadruple stars. So you're trying to make a connection with metallicity, and yes, metallicity will be important for a single star, and of course, the conservation of angular momentum that you may have at the origin will depend on this. But if you have binaries, binaries can do all sorts of tricks. And so how do you think that would come in with metallicity?
With metallicity, in my view, I'm not a modeler in particular for binary star, because there are so many parameters to take into account, like the mass ratio of the binaries, what is the role of the stripping in this event. And from an observational point of view, I will go more in observing the region where these stars form, because they form in this H2 region whose life is of the order of 100 mega years, if not more. And I remember that both in the case of a single star, but also in binary stars, particularly in binary, the life of an exploding star can be shortened by the presence of the binary because of the stripping event, and can collapse before. So measuring the metallicity from each region can be the best way to have an idea of the original metallicity when the stars were formed. I can tell you that actually there is this trend that binary makes everything works perfectly, but I also know that binary, when you use these binary stellar templates, it is expected that there are some differences when you use these codes to infer parameters from the stellar propagation. But there are other models involving single star, this chemically homogeneous evolution that can also lead to a low metallicity core in some cases. So I found problems in understanding what is the best channel to consider. So my approach consists just in using an observational, taking data and inferring properties from observation. Probably I did not answer your question correctly, but this is what will be my approach.
Okay, thanks.
Okay, Diego, please.
Vale, so actually it's two questions, but I'll ask the first one. So your last supernova, the 2022 EQ So this is not linked with a GRB, right?
No, there is no known GRB associated with this.
So as an observer, how do you know how that in this one there will be a cocoon? Like how do you know to which supernova?
Actually, I'm still working on this, but in general, when you observe, if you look at general the evolution, the light curve of 1C core collapse supernova, you do not expect a prompt rising phase. You just expect a initial exponential rising followed by a more shallow decay. Here you have a prompt rising, then Swift, the data that we got Swift shows a secondary rising phase, suggesting that it was a pre-supernova band. But another evidence that there was a cocoon, like for 1C broad-line supernova, is that our spectrum obtained almost 20 days from the discovery shows velocity of 25,000 kilometers per second, which is not typical to observe in normal 1C supernova. To be honest, we are still trying to understand this source. Probably it's not a 1C broad line, there's no cocoon, but I would like to show you this case because it could be something that can be of interest also for you or for other people here.
Okay. And then I see that Fabian is in raise their hand, so I'll ask the last one. So, I mean, one reads papers or reviews of GRPs, and I was normally accustomed to hearing that the supernovae that are related with GRPs are, and they always put supernova 1B/1C. But so what you're telling us is it should be supernova 1C broadline.
Yes.
Okay. So every time now that I put in a conference, the supernova, it should be supernovae broadline, 1C broadline.
1C broadline, yeah, actually it's wrong mention 1B because in 98, in the first GRB supernova 98 BW, there was a paper by Nando Patat, if I remember correctly, where he found an absorption line that he attributed to helium. And then there was another paper by Paolo Mazzani mentioned that was not helium, but was magnesium-1. But if it were helium, that would be our type 1b supernova. The fact is that in also in the supernova, unfortunately, I do not have a slide here with me. In the supernova in 2017 IUK, in the paper, and it's not shown here, but on the day 7 or day 10, we found a similar absorption line that could be interpreted as helium. It is reported in the paper, but we did not develop the point. But in general, all supernovae associated with GRB show these broad line features, broader than a normal 1C supernova. That suggests that there is a larger velocity dispersion and higher expanding velocities of the eject than the presence of a central engine.
Okay, so Nisim, go ahead.
Okay, thank you, Leonardo. Okay, thank you, Luca. Was a nice presentation. Just, I have a quick, several questions. Let me introduce and organize. Okay, you told us about the GRB 1904-25, the supernova associated with the GRB, also 03-03-29, GRB 06-02 18, excuse me, and GRB 10-03-16D. Okay, you mentioned there are two proposals. One is the off-axis emission, and the other is the shock breakout emission. So you mentioned in the GRB 06-02-18 and the other 10-03-16D, the T90 was more than 100 seconds, okay? And the previous one was less than 20 seconds. So that was completely different, and the energy was completely different. So, and you mentioned about also the 1712.05a. So you could imagine a model to reconcile all these situations, because the T90 was completely different. When you do the soft and hard test, okay, that are completely different of the prompt emission.
Yes, I don't remember now 100316D, but I remember that there was an X-ray flash associated with the 2020 BH supernova. I should go back to that JP, but in any case, 060218 and 171205 have two main different observational properties, that it's their X-ray light curve. So this is the X-ray light curve of 060218, showing a very prolonged emission lasting 10,000 seconds until there was the late power law decay.
So usual afterglow, okay.
Yeah, exactly. While 171205 did not show this long emission and thermal component, just a canonical power law behavior, pointing out that there was a jet that drove the supernova of axis, slight of axis or not, but there was a jet. There was another model here proposed by Ehud Nakar for 060218, which, however, we cannot verify that this emission is actually the cooling of the circumstellar medium that has been shocked by it's a paper by Huda of 2015, by the shock breakout emitted by this event. However, why cannot be verified? Because if we have an extended wind,
yes, larger than 10 to 14 centimeters. Okay.
Exactly. I think there's an extra slide. In case we should observe in the early optical spectrum some feature, like for example interacting supernovae, like type 2 supernovae. Sorry, I'm going a bit quick. Some feature of the properties of the wind surrounding the progenitor star. And very recently, the ZTF group has discovered this type 1 CN class of supernova 1A, which is characterized by the presence of P Cygni profile of carbon and oxygen features.
You mentioned that it's a collapse of the CO star, probably?
Well, you have a collapse of the Wolf-Rayet carbon oxygen core, but then if it's surrounded by a very dense thick medium, you have that the ejecta start to interact with this medium that can emit not only, X-ray radiation due to the interaction, but you should observe some features in the optical as due to the interaction of the ejecta with the
wind, star wind.
With the wind, exactly, with the carbon that is rich in carbon and oxygen. Unfortunately, for this supernova, we do not have spectra this resolution to reject or confirm this hypothesis. My idea is that it is possible that 060218 was, as Nakar, but it's only my idea, as Nakar mentioned, was surrounded by a very thick wind, and his modeling of the X-ray emission agrees with that, but the smoking gun would have been the detection of this narrow feature, confirming that the presence of this massive wind, extended wind, rich in carbon and oxygen, and also neon, depends on which
Okay. Well, this is associated with the next question. You mentioned, and I know that a thermal emission, KB thermal emission, that's different from the supernova emission. The first one was on time scale of 1 second, 100 seconds, excuse me, and the other was a days. Of course, I didn't understand the Galama's paper, because they say that was associated with a wind, a mass, stellar wind mass with 10 to minus 7 solar mass. So that's completely light. That's, yes, and the supernova is associated with that 10 to minus 2 or 10 to minus 1 solar mass. Of course, the first one could be associated with a cocoon emission, probably. Have you tried to model with that the first thermal emission?
You mentioned 98 BW in the Galama.
Exactly, exactly. The first was a KV. So you mentioned if you put again the light curve, the JRB, this is the 060218 light curve. You mentioned that it's a black body component. Okay, this the black body component. When the paper said that the thermal was 0.3 or 0.5 kV. Okay, yes. But that is completely different from the optical black body. They try to relate both black body components with different mass. Okay.
But this is in 98 BW or in 2006 AJ, because
here is a black body component. Of course, it's in kV, and the peak is 0.4, 0.5 kV. Okay, okay. This is one thermal component. But in you have other. This one, you have other component in optical.
Well, actually, you have this thermal component.
Exactly.
Well, actually, the temperature, like in 171205, is moving at lower energies than the peak of the black body, according to the Wien law, moves also to longer wavelength. So the black body from here moves here.
No, this is my question. You believe that? I think that
I believe, yes.
People try to connect the KV with the optical, yes, but in both cases use different mass assumption. That you could say, okay, you have a cocoon component, and the other is a supernova component.
Why are you saying that you have different mass components? What are the masses in the two cases?
Yeah, exactly. That try to relate both, yes, but with different kind masses. But okay, don't forget. And in the future we can discuss.
Is it not just a single component, just cooling with time, and you move to lower temperatures with time? It doesn't work.
This is my question. That they assume that when it's a typical thermodynamics, no? That you expand and cool down.
The shockwave expands, it cools.
Exactly. But the mass change. That the mass is not equal for both. But okay. Okay.